Welcome to Mootechie. Today we are exploring the fascinating world of heat transfer, a topic that is essential in engineering and especially in the food industry. Let's begin our journey through the basic heat transfer process. Moving to next slide. Introduction to heat transfer. Heat is the form of energy that can be transferred from one body to another cooler body as a result of a temperature difference. The science that deals with determining the rate of such energy transfers is called heat transfer. Moving to next slide. Heat transfer in the food industry. Heat transfer is vital in food processing technologies like baking, drying, sterilizing, and freezing. Knowledge of heat transfer is essential for designing and controlling heat transfer equipment used in the food industry. Moving to next slide. General rules for heat transfer. Heat transfer occurs only if there's a temperature difference between two bodies. Heat always flows from a hot body to a cold body. The heat lost by the hot body equals the heat gained by the cold body, assuming no losses to the surroundings. Moving to next slide. Rate of heat transfer, driving force and resistance. The rate of heat transfer equals the driving force divided by resistance. The driving force is the temperature difference. Resistance includes factors like the thickness or length the heat travels through, area of heat transfer, thermal conductivity, convective coefficient, and shape factor. Moving to next slide. Modes of heat transfer. There are three primary modes of heat transfer: conduction, convection, and radiation. Moving to next slide. Conduction. Conduction is the transfer of heat through direct contact between particles. In gases, it occurs through molecular and atomic interaction. In fluids and solids, it's through elastic molecular collisions. In metals, it's mainly due to the diffusion of free electrons. An example is heat transfer through the solid wall of a refrigerated store. Moving to next slide. Fourier's law of heat conduction. The rate of heat conduction is directly proportional to the temperature difference and heat transfer area, and inversely proportional to the thickness of the layer. The constant of proportionality is the thermal conductivity of the material. The negative sign indicates that heat transfer in the positive direction is counted as a positive value. Moving to next slide. Thermal conductivity. Thermal conductivity is a property of the material. It measures how well a material can conduct heat. It is defined as the rate of heat transfer through a unit area and thickness in unit time, given a unit temperature difference. Materials with high thermal conductivity, like pure metals, are good conductors. Materials with low thermal conductivity, like cork, are good insulators. Moving to next slide. Factors affecting thermal conductivity. Factors include material structure, moisture content, density, pressure, and temperature. For conductors, conductivity usually decreases with temperature. For insulators, it increases. In gases, it also increases with temperature due to higher atomic activity. Moving to next slide. Variable thermal conductivity. Thermal conductivity often varies with temperature and is given by the formula K equals K naught times 1 plus B times T dot. Here, B is an empirical constant and may be positive or negative. B is positive for nonmetals and insulators and negative for most metals. Moving to next slide. Isotropic and anisotropic materials. An isotropic material has the same thermal conductivity in all directions. An anisotropic material has different conductivity depending on the direction of heat flow. Moving to next slide. Convection. Convection is the transfer of heat between a solid surface and a moving fluid due to a temperature difference. It involves both conduction and fluid motion. Faster fluid motion increases convection. If there is no fluid motion, the transfer happens by conduction. Moving to next slide. Types of convection. Natural or free convection occurs due to buoyancy forces caused by temperature-induced density differences, like cooking without stirring. Forced convection is when a fluid is moved by external forces like a fan or pump, such as cooking with stirring. Moving to next slide. Newton's law of cooling. This law helps calculate convective heat transfer. It states that the rate of heat transfer equals the convection coefficient times area, times the difference in temperature between the surface and the surrounding fluid. Moving to next slide. Convective film coefficient, also called the film heat transfer coefficient. It is not a property of the fluid, but is determined experimentally. It depends on surface geometry, nature of fluid motion, fluid properties, and bulk velocity. Moving to next slide. Radiation. Radiation is the transfer of energy in the form of electromagnetic waves, or photons, due to changes in electronic configuration of atoms or molecules. It doesn't need a medium. It is the fastest method of heat transfer and travels at the speed of light. Moving to next slide. Radiation real-world example. The sun's energy reaches Earth through radiation. All substances emit, absorb, or transmit radiation to some extent. Solids like metals, wood, and rocks emit radiation mainly from their surfaces. An example is heating food using an electric grill. Moving to next slide. Stefan Boltzmann's law. The law states that the radiation emitted by a surface is proportional to the fourth power of its absolute temperature. Q equals shape factor times sigma times area times temperature to the power of 4. For a black body, emissivity equals 1. Moving to next slide. Net radiation heat transfer. The net radiation between two surfaces is given by Q equals shape factor times sigma times area times the difference between T1 to the fourth and T2 to the fourth power. Moving to next slide. Combined modes of heat transfer. In real-life applications, conduction, convection, and radiation often occur at the same time. Heat may also be generated inside solids. For example, when heat flows from a hot fluid to a cold fluid through a barrier, conduction and convection happen together. Moving to next slide. Heat transfer example, plate and air. Imagine a hot plate at 77 degrees Celsius with air at 75 degrees flowing over it. Heat leaves the plate through a combination of convection and radiation. So the total heat loss equals convection plus radiation losses. Moving to next slide. A very tall heat transfer coefficient. When heat transfers between fluids across a metal wall, the overall heat transfer coefficient is used. It's calculated using the formula 1 over U equals 1 over H1 plus L over K plus 1 over H2, where H1 and H2 are convection coefficients, L is the thickness, and K is the thermal conductivity. Moving to next slide. Equivalent radiation coefficient. Radiation and conduction or convection can happen at the same time. To find the equivalent radiation coefficient, use the formula Q equals HR times the temperature difference. When the temperature difference is less than 100 degrees Celsius, average temperature can be used in the formula. Thanks for watching Mootechie. We hope this deep dive into the basics of heat transfer helped clarify your concepts. Don't forget to like, share, and subscribe for more simple and effective explanations. Until next time, keep learning and stay inspired.